Okay, this is a walkthrough of a conservation of mechanical energy problem where we're dealing with spring forces. So let's say that we have a cart that's able to roll along a horizontal surface. And let's say it has a mass of 0.2 kilograms. And it's connected to the wall by a spring. And this spring has a spring constant, K, that's equal to 100 newtons per meter. And let's say that we pull the cart back to the left 0.05 meters from its rest position, the spring's resting length. And release it from rest. Then the question is, how fast is the cart moving when it's 1 centimeter from its resting length? Okay, so we're going to pull it back 5 centimeters, and then we're going to see how fast it's moving when it's 1 centimeter from its resting position. By the way, these motions are always symmetric around the resting position. So if you pull it back 5 centimeters, it'll, you stretch it out, it'll move back until the spring is shortened 5 centimeters from its resting position, and it'll oscillate back and forth like that. And any answers you get are for the speed are going to be the same answers you get on both sides of the resting position. So this answer we're going to get would be the answer when the spring is stretched 1 centimeter past its resting position, and when the spring is compressed 1 centimeter past its resting position. That's always the way these problems work. That's just the way spring motion works. Okay, so the first thing you have to do is think, does conservation of mechanical energy work for this? Remember that the kinds of forces we can deal with are weight, spring forces, normal forces in rolling and sliding, and centripetal forces in circular motion. If you think of a free body diagram, you have the spring force, you have the weight force, and you have the normal force. And those are all in that category. So yeah, this'll work. The other thing that we have to do is, whenever we're dealing with gravity, we have to choose a location that we're going to call our height equals 0. And you just have to be consistent through the problem. We might as well choose that height equals 0 to be the height that the thing is at, this cart is at, through the whole motion, because that'll just make the spring, the gravitational potential energy go away at every instant we do. So we won't see it in the equations. You could choose any height though, and what you would see is that in the end, that gravitational potential energy canceled out. So it wouldn't affect the problem no matter what you chose as your height equals 0. This will just simplify the look of the equations a little bit. Okay, so our instant 1 is going to be when the spring is pulled back 5 centimeters, and our instant 2 is going to be when the spring is 1 centimeter from its resting length. So pause the video for a second and see if you can fill out this table. Okay, so the gravitational potential energy is m times g times h, which is 0. And so, like I said, this is just going to be 0 at every instant in the motion. You see it there. Now we'll go to the spring potential energy. That's equal to 1/2 times the spring constant of 100 times the deviation from the resting length squared, so that's 0.05 squared. And if you calculate that, you get 0.125. And this is a kind of energy. We're an SI unit, so the units are joules. I guess I'll put that in here. And last, we have to come up with the kinetic energy at instant 1. Well, at instant 1, we're releasing this thing from rest. So we have 1/2 times the mass of 0.2 kilograms times the speed squared. The speed is 0 because it's at rest. And so the kinetic energy is 0 at instant 1. Now we have to go through the same thing at instant 2. The gravitational potential energy, I guess this time I'll fill in what m and g are, but we're going to get 0 just the same way. So we have 0.2 times 9.81 times 0, and so this is equal to 0. And now the spring potential energy is 1/2 times 100 times 0.01 squared, because our deviation at instant 2 from the resting position is 1 centimeter. And if you calculate that, you get 0.005 joules. And then the kinetic energy, well, we're trying to calculate this speed, so we don't know what capital V is. So we have 1/2 times the mass times V squared. And so that's just 0.1 V squared if you simplify that. And so finally we can go to conservation of mechanical energy. We have 0 plus 0.125 plus 0 is equal to 0 plus 0.005 plus 0.1 V squared. And so we get, if we subtract 0.005 from both sides, we get 0.12 is equal to 0.1 V squared. Multiply both sides by 10, and we get 1.2 is equal to V squared. Take the square root of both sides, and you get V is plus or minus 1.10 meters per second. This is a speed, so we want the positive one. And so this tells us when this cart is 1 centimeter removed from its resting position after you've released it, it'll be going 1.10 meters per second.